Hi everybody. A little recap since we've had a weekend off. A little recap on Newton's first and second laws. I know we've covered them on positive physics, but I kind of want to talk about them just here once again to kind of get the gears turning going into a new week. So Newton's first law stated that an object at rest will stay at rest, and an object in motion will stay in motion at a constant speed, as long as there's no net force, no unbalanced force. So that means you'll either stay at rest or continue at constant velocity if there's no unbalanced force on the object. Now another name for an unbalanced force would be a net force. So in other words, there's no net force. You have all balanced forces. Your object is going to either stay at rest or continue moving at a constant velocity. We say that if there's no unbalanced force, that the object is in a state of equilibrium. It's not speeding up, it's not slowing down. The object is either sitting still or moving at a constant velocity. Let's take a look at a couple of examples. You got an object here that there is a person pushing to the right with, let's say, 10 newtons of force. That's an applied force. Our object is 5 kilograms. And we'll say that the object doesn't move. The person's pushing, but it doesn't move. Well, what does that mean? That means there has to be some other force to the left keeping it still. What would that be? That would be friction. And if it's keeping it still, it has to be the same as that applied force, 10 newtons. There happen to be two other forces acting on this object. One of them is the weight of the object pulling it down. Now the Earth pulls 1 kilogram, every kilogram on Earth, down with 10 newtons of force. So if you do 5 times 10, you get 50 newtons as the weight. And the ground is supporting this object, not letting it go through the ground. So the ground, this normal force pushing up, has to also be 50 newtons. So if you take a look at our object, the left and right forces are balanced. The up and down forces are balanced. Our object is in equilibrium, and therefore it has two options. It can either be at rest and staying at rest, or it could be sliding at a constant velocity. Here's one more example for Newton's first law. What if I give you the free body diagram? Let's say that there's there, force there, force there, and force there. Got these 4 forces. We don't need to know numbers. We can say that these guys are the same. Could this object A, be speeding up? The answer to that, you have to look at the free body diagram. Right now it's in equilibrium. The up and down force is balanced, the left to right force is balanced. Our object is in equilibrium. Being in equilibrium means there's no net force, which means our object can't speed up or slow down. Okay, it's in equilibrium, so this answer is no. Question B, could it be sliding to the right? The answer to that is yes. If it was, it would be sliding at a constant velocity. That's one of the terms of equilibrium, one of the options. It's either sitting still or moving at a constant velocity. So if it was sliding to the right, it could be a yes, but it would have to not be speeding up or slowing down. Now let's talk about what happens if the forces are unbalanced. Well, now we've moved on from Newton's first law onto Newton's second law. So if you have unbalanced forces, that means there is a net force on the object. Whichever direction has more force, that's the direction the net force points. Net just means total. So if that total is not a zero, you have an unbalanced force, which means the object accelerates. So it either speeds up, slows down, or turns around. The object cannot either remain motionless or go at a constant velocity. That's not an option when you have an unbalanced force. We also have a math equation that goes with unbalanced forces. It's what Newton's second law states. And that is that the net force on an object is equal to the mass of that object times its acceleration. Let's look at an example. Let's say you've got a 2 kilogram object here. You've got 4 newtons pulling to the right. You've got, let's say, 2 newtons pulling to the left. And I want to know what's the acceleration of this object. Well, we're missing a couple of forces. You've got the weight of the object pulling down, which would be 2 times 10, or 20 newtons for the weight. You got the ground pushing up, that would be called the normal force. And it would be the same as the weight, because it's not moving up or down, just left or right. And we see that our forces left and right are not balanced. You have more force to the right than left. So we first of all have to determine the net force. Oops. So the net force is the however much unbalanced force you've got. You got 4 to the right, you got 2 to the left, so since they're in opposite directions, you subtract. You got 2 newtons to the right as your net force, or just 2 newtons. Mass of our object is 2 kilograms, so if I do F net equals ma, I've got 2 equals 2 times a. That gives me an acceleration of 1 meter per second squared, and that would be to the right, whatever direction the net force points. That's the direction of the acceleration. One more example. Let's say that there's a person that's falling from a plane. They pull their parachute. Pretty bad parachute drawing, but you get the gist. We'll say that the person's mass, along with all their gear, is 100 kilograms. And let's say that their acceleration downward is only 8 meters per second squared. Yeah, that's kind of a lot. Let's go with 2 meters per second squared. Okay, if they were just falling without a parachute, it would be 10, would be their acceleration, but the parachute's slowing that rate down to 2. And I want to know how much drag force is there on the parachute. So if I draw the person as just a dot, I've got the weight of the person pulling down. I've got the drag force pulling up. But I don't have anything left to right, and that's totally fine. I know that the weight down has to be bigger than the drag up because our person is still accelerating down. So I can draw that arrow a little bit longer. So in order to do F net equals ma, I need to get the net force on my person. So what's the weight of the person? Well, their mass is 100. Multiply that by 10, that would be 1,000 newtons pulling down. Drag, we don't know. But I can do the net force equals mass times acceleration. So I've got 100 kilograms, and I've got 2 as my acceleration. So the net force is 200 newtons down, which means there's 200 more newtons pulling down than there is up. So what does that make the drag? It's either 1200 or 800. Since the net force is down, the drag is a little bit less than the weight, making it 800 newtons up. So that the net, the total, is 200 newtons down.